Okay, well, just gave back some homework. And I have a few comments. I have one big comment that I would like to make. And this comment is about how you checked the range of the number that you did for the hexadecimal number, all right? Because they were all incorrect. I mean, it's an incorrect approach.
That's this one?
The one that I just handed back.
Oh.
Yeah, actually.
You're having the trouble with me because I don't have it.
Yeah, actually yours was incorrect because you didn't make the check at all. But most people made the check, but they made the check the wrong way. Now, here's what most people did. The problem was to write a program that would parse a hexadecimal value and make sure that it was not bigger than FFFF, right? And the way everybody did that is they had a finite state machine that ignored the leading zeros, and once you got a character, there was a state. You had a state for accepting the first character, and a state for accepting the second, and a state for accepting the third, and a state for accepting the fourth. Are you with me? And then if it accepted more than that, then it was an error. But that is not, I'm glad we're getting this cleared up, because do not do that with your project. That is the incorrect way to check for the value of the hexadecimal constant. And here is why. I mean, it works in this case, but only because we're dealing with hex and we know how many digits. And here is why. The reason is because you also need a way to check the range of a decimal number. But the range of a decimal number in your assembly language program is not dependent on how many characters there are in the string representation of the number. Are you with me? And not only that, but you have a plethora of states the way you did it. You see what I mean? You have way too many states. Okay, so, and in fact, if you read the specification in the, was it on the web page or was it?
It's on the web page.
It was on the web page. It said check the it said check if the value is what? Greater than 65,535. That's how you check it. And nobody actually checked 65,535, the value. Oh, you did?
Mine didn't go.
But why, huh?
Mine didn't go past it.
Yeah, I know it didn't go past it, but why all those states? No. I know you did it, but you did it by virtue of the number of characters.
But I checked it in my while loop.
I know.
If I checked it in my while loop, like in the do loop, like that was one of the requirements.
I know, but the way you did it is you had a state for each character. What I'm saying is, don't do it that way.
Is that less efficient too?
Well, for one thing, you have a multiplicity of states. You don't need that many. You don't need, and not only that, but that technique, the way you use that technique will not work whenever you have decimal constants in your project. Do you see what I mean? So you should use a more general. You should use a more general technique. And what you should do is, and I'm saying this because your next assignment, which is to do the, don't do it this way for this next assignment. All right. So here's what you should do. You should actually literally compare it.
To see if it's greater than.
To see if it's greater than 65,535. If it's greater than or equal to 65,536, at the end, just once, then for this program, after you get through doing it, you see if it's greater than that, and if it is, then it's automatically invalid.
That's so smart.
Wait.
And then you don't need all those states. That's what I'm saying. You don't need all those states. No.
You have what, 2, maybe 3?
Yeah, maybe 2.
Yeah.
But then couldn't you have?
You could have had maybe, huh?
Couldn't you have more than 4 like inputs then?
No, because.
But it's all right because the zeros it would keep doing the leading zeros just like it did before, and
But what if they weren't leading zeros?
Well, here's what you have to do. Here's what you need to do. You need to, for example, okay, and actually, before we go on, I want to show you, I want to do a demo. I have a demo for you, okay? So you ready for this? Mm-hmm. Demo. All right. Now, watch this.
Would you still need another state for the 0 case? For like
No, the start, yeah, you would need the, yeah, you would. Well, would you? No, I don't think so. No, I don't think so. Yeah, it will just go, yeah, no, I don't think so. Okay, hold on.
Okay.
Okay, so here's the demo. And this demo uses a library. Its name is limits, okay? And so in this program I have included limits. I just wrote this up right before class to illustrate the point, to make the point of because of this homework issue. Okay, and what limits does is it provides you with a function that will return the maximum and minimum values of your, of an integer, for example, in this case. It can do also for real, doubles and so on. Okay, so here, look at this first line. This first line right here says cout, minimum value for int, and it's the function is called it's numeric limits typecast to int : min. So min is the function that it supplies an inline. So what this output will be minimum value for int, and then it will print the minimum value for int. And this depends on my computer. Mm-hmm. Right?
Right.
I mean, because each computer, a small computer, big computer, it depends on how many bits. Well, I mean, we know about how, what's the range of integers and it uses 2's complement binary representation, right?
Yeah.
Okay. Is everybody with me on this? Yes. Okay. And then here it will do on this line, it's going to do the same thing for the max. All right. Then what I do is, what this program does is, it says int I gets numeric limits, so it sets I to the maximum integer value. Mm-hmm. Are you with me? And then we're going to, just to make sure, we're going to cout I equals, and the value of I. And now what are we doing here? Adding one. Now we did this at the beginning of the course. What happens if you add 1 to the maximum positive value? It becomes 1, 0, 0, 0, 0, 0, 0.
Right.
Which is what?
Zeros. All zeros.
No. 1 in the sign bit and all zeros.
The most negative number.
Where's that?
It becomes,
Yeah, it becomes
the
the
most
lowest
negative.
number in the range.
Yeah.
Plus it just wraps around.
That's the point. Mm-hmm. That's the point. It'll just wrap around. And so what do you suppose this will? And so now after we add 1 to it, now what's going to happen?
That'll be the minimum.
Yeah, so watch this. This will be a nice demo. Check it out. Minimum value, -2 for blah, blah, blah. Maximum value, 2 for blah, blah, blah. So I set I to the maximum value. 21, 47, 48, 36, 47. Add 1 to it, what do I get?
The negative version of it.
It doesn't crash. It just wraps around. So do you see that if you were parsing an integer, and you had a really long line of numbers, and each time you go through it, what do? You multiply it times 10, and then, are you with me? Mm-hmm. You multiply that digit by 10. You multiply the current value by 10, and then you add the numeric value, to it. What will eventually happen if you have so many digits? It'll wrap around. It will wrap around like this. You have to know that. You have to understand that that's what it'll do.
So we were keeping it from doing that.
And what you need to do is, yeah.
Because we want correct results.
Right. Well, yeah. So here's what you have to do. So actually, that's the demo. So there's the end of the demo. Okay, so that's the demo. Now, so to get back to your project, what you need to do is, here's the problem. Every time you do a multiply by 10 and add, every time you do that, you need to check to make sure, after you do that, you need to have an extra guard that checks to make sure that at that point, that value is, if that value exceeds the maximum, then that's where you make it an invalid. That's where you make it invalid. And therefore, you don't need any extra states, because you know what the limit is supposed to be.
We don't have to do it in hex 1 or int 1, do we, in those two states? We do it in int 2 and hex 2.
Okay. Now let's look. So anyway, you see how, before we go on. So does everybody see how it would have been better? I mean, how that's a better way to check for the thing, the limit. Okay. So now let's go to figure 7.50, which is from the exercise section of the book, and take a look. This is the finite state machine that you have to implement for Monday. This is your, and I hope you've started it. Okay, because I warned, I was encouraging you to start this. Okay, so I hope you've started it, and you might. And it sounds like we have some questions, which we'll answer here in a minute. But before we do that, now your question was, which states do we have to do that in? Okay, so let's take a look. Here is our. So if we have a decimal, an integer, and we start in the start state, and you asked about hex.
In int 1 and hex 1.
Yeah, okay, so if it's a leading 0, you're going to go to int 1, and then if it's an uppercase or a lowercase x, you're going to go to hex 1, and then if it's a digit, you're going to go to hex 2. It's only when you're in hex 2 that you have to have that test. Because see here, we don't want to have a hex 2 and a hex 3 and a hex 4 and a hex 5 to make sure that we only get 4 digits after leading 0. You see, that would you see, if you did it the way you guys had done your homework, I mean, can you imagine they'd have a plethora of states. We don't want that. I mean, we want to make it as less complex as we can. Okay, and similarly, let's think about the int. So you would go from the start, so on a 0 you'd go to int 1. You don't need to check it for int 1 because that's just 0, right? And then a digit will take you to int 2. So int 2 is where you should have the check for the integer constants. And furthermore, that int 2, you see in assembly language, there's a negative to a positive. See? So that's where that test would be in int 2.
Same test, right?
Same kind of test. The decimal values are different because you can have signed.
Yeah,
Signed what? Both of them?
Well, because you can have signed constants in assembly language.
Okay.
You can have signed decimal constants in. For example, here, if you say this, if you say load accumulator -5 immediate. Or here, let's make it a bigger one. If you say load accumulator -562 or 5, what is the range? What's the negative range?
-32768.
5264 immediate. This is going to be out of range, right? But what you have to do is each time you check a digit, you got to make sure that it's in range.
Every time.
Every time, because otherwise what could happen? You have to do that every time. Why is that? That was a really good observation.
Otherwise, I guess it could wrap around.
It could wrap around and all of a sudden be in range and you wouldn't know it.
So then I have a comment. So when you're doing your direct code, we're in int 1, so we read in a 0.
So we're in int 1 and we read in a...
So we go,
Oh yeah, we read in a 0 and went to int 1.
Integer,
Yeah.
Get 0,
Yeah. Notice that, and notice that int 1 is a what kind of state?
It's a final state.
It's a final state.
Yeah, it's a final state.
Yeah.
So we could go in there and say, okay, we have 0. Or, I mean, you were saying we only need to check it in int 2 or hex 2?
You only need to check the range, out of range problem.
Can't int 1 only be a 0?
Yeah,
So you don't have to check the range.
correct.
But what if, okay, and this is a better example in hex 1. If we go to hex 1 and we have just...
So you have just scanned a 0 and an X, and
Yes.
you're in hex 1.
Okay, and then we add some other digit.
What do you mean, other digit?
Just any, like a digit. We get a hex digit.
Hex, okay, like A.
Yeah.
That will take you to hex 2.
And I guess that digit's guaranteed not to be out of range, right?
Well, of course.
Okay.
One hex digit,
why we don't have-
one hex digit,
Okay.
you don't have to check for the range.
Because it's possible we get to hex 2 and then never even go to the adding another digit, so we don't check the range ever. But we don't need to.
But you check the range every time.
But no, well, you check the range if you're in hex 2 and you get a hex digit.
Right. If you're hex 2,
You
you're not-
multiply times 16 and add the thing, and then after you do that, you make sure that it's in range.
Okay. Now,
I
question.
mean, because do you see, if you had a long enough string, you could have this wraparound thing and think you're in range when really the user put a long old string of characters. I'm telling you guys, this is the kind of thing that separates the pros from the amateurs. I'm telling you, this is the nitty-gritty. You got to think about stuff like this. Yeah.
So explain to me how, after it reads the last digit 4,
Mhm.
which is out of range, which would make the whole thing out of range. How does it not wrap around already?
It would have.
That's
Oh,
because
no,
like,
it wouldn't.
Well, yeah. The test is going to be kind of sophisticated here because, I mean, you have to be, because at this point you have not multiplied it by sign yet. So you have to know what sign is.
It's actually in range if you don't have sign yet.
Yeah.
Ask about-
It's actually in range if you, so it's going to depend on the sign. The test is not going to be simple here because as you're parsing it, you haven't multiplied it by sign yet.
Is it okay?
But you will know what sign is.
We only have to worry about sign in int 2, not hex 2, right?
Correct.
Is it okay to implement sign in the sign state in that case? Because that's what I did to fix that problem.
What do you mean implement sign?
So in case state sign,
In case,
so you go to start, you either get a plus or a minus, and you go to sign. And when in the start case is where sign either gets -1 or
plus one, yeah.
So then when you're in case sign, I went ahead and changed the digit to be negative or positive there, and then moved on.
No, I don't think that works because you have to add. Then you would have to subtract each time you went through.
If it's
Are you with me? Yeah. See, you would have to subtract each time you went through.
Okay.
Yeah, oh, I'm glad you saw that now.
Or you could add the value times sign.
Yeah, but then you'd be multiplying times sign every time through the
Yeah.
loop. It's better to add it it's better to multiply it times sign once at the end.
So then,
So you just
But that's going to make this test a little more complicated, but you can think through that. Huh?
If we get all of the tests on the website to work, are we solid?
You are pretty solid, but no, the answer is no. You are not 100% solid.
because all my tests worked, and I did that wrong.
Really?
So,
And all the integer outputs and everything were the same?
I think so. I should just check them all.
Did I not have an example of a negative
I don't
value?
think you did.
You must.
Oh, I think I didn't.
Because then otherwise.
Yeah, I think I did not. So you're going to have to make sure that the tests work. And here's what you guys should do. Actually, the reason I on purpose did not have an exhaustive unit test because, last semester in data structures, I gave you all those unit tests. Oh yeah, I passed the unit test. Boom. But now, designing the unit test. That's yet another software engineering skill that you need. And let's think about that. Which values should you always test? You should always test the boundary values. Are you with me? So what you should do for the negative numbers, you should try a negative number that's exactly within,
That is at the very end.
that is at the very end, and then the one that's one more. To make it out, to make it beyond it. So you should check, and same way at the plus, and the same way with all those, to make sure that it works exactly, precisely, correctly. Those are called the boundary cases. See, this is the kind of thing that these kinds of projects, you can only, it'd be hard. it'd be hard to kind of like read about all this stuff and then you just have to do it. You have to write a big project like this and then come across all these ideas.
Can I ask, what are the rules for the spaces for this part of the project? Because I got a little confused about all this.
Well, no, I mean, the spaces are all taken care of in this finite state machine. Why is that any different from what we had done in the previous assignment?
I think just in the major assignment, there were more extra rules about spaces, maybe for later on, and maybe those aren't. Did you remember reading something?
I think, I see what you're saying. I think if you just implement this machine exactly the way it is in figure 7.50,
It'll be.
this takes all of that verbiage into account. In other words, this is an implementation of all those rules.
Okay.
Only thing is, well, except for the fact like this, well, never, yeah, no, that's, yeah.
This might be a similar question, but in the book it says we have to enumerate what our
The addresses?
tokens are.
Oh.
It says you need to enumerate
Oh,
ET,
we were talking about
identifier, ET.
Yeah, you still have to do that.
Do we have to do that as well as having all these states for
No.
tokens?
No, yeah, oh, hold on, whoa. Don't you remember in that example that we did before, we had an abstract
Right.
token
Abstract tokens.
and all those other ones?
Tokens.
That's what you do.
So that's what that is. We don't actually have to have a tokens class that.
You have an abstract
Right.
token and you have those specific ones with their attributes that you need.
That was the same question I had earlier because I thought we had to make states out of them.
Right.
No, hold on. States are not the same thing as tokens.
Right.
Then
I
the
mean,
oth-
sorry, a class because they said make a class, but it was C++.
Yeah.
So
So
it's different.
the other question I had was on the website. It says addressing modes must be stored as identifiers.
Oh, good question. Good. I'm glad you brought that up. Now, watch this, you guys. So here comes another thing. Look, what you could do, let's make this legal. Negative 562, comma, immediate. Another one could be load accumulator, negative 562, stack relative indexed. What's the longest one? Load accumulator, negative 562,
Is that
SFX,
SXF.
XF. Yeah, stack index deferred. This is called stack index deferred addressing. Okay, now look, one way to do this, now here we go. You could have a plethora of states, right? And so for an addressing mode, you could have, S, because, you could have an S you could have a D for direct addressing, you could have a
Okay.
an I for immediate, you could have, for whatever, and then you'd have an S, and then you'd have an S, and then you'd have an X, and you had states all over the place.
Okay.
Are you with me? And be a final state for each one if it was illegal. But look, I mean, you'd have states multiplying all over the map. So here's what we're going to do. What we do is we notice that this has the an addressing mode looks like, and for all practical purposes is, an identifier because it starts with a letter and it's a string of letters and digits.
But it always follows a comma.
Yeah. Oh yes. But look, Gene. Oh yeah, you do know that it's an addressing mode because it does follow a comma.
So we made each of those states a different case. Is that okay?
Yeah, that's how you have to do a finite state machine.
Specific token class for every end state.
Yes.
Yeah.
Even the address mode.
Yes.
Okay.
Yes. And even the
So I need to start one.
And we don't want any more or less states than what we have in the
I insist that you must have do exactly this finite state machine. There's only one more state that should be in here, and that's what?
or stop.
Stop.
Stop. Yes.
And furthermore, there should be one token. There's a list of tokens, isn't there, in the book?
Yes.
Yes.
And let's count. How many tokens should you have? How many tokens should you have?
7?
Yes. Oh, plus one more.
7?
For what?
Invalid?
For invalid.
So we do need a start token.
No. That's not start. You don't call that
It's
one start.
empty.
That's
That's
the
empty.
empty token.
Okay, so
That's
we have
the
that.
empty token.
Okay.
Yeah?
Yep.
Boy, I'm sorry that I steered you wrong a few times before I had to take back.
You could just cut that
I
off.
could cut that out, but I don't think I'll bother.
Teaching on it.
Yeah.
Start with the left hand side.
Yeah, that was classic. Yeah.
We literally spent so long.
Editing is just wonderful. I have at the Academy Awards. I have a new appreciation for the Editing Academy Award.
Empty that.
You can cover a multitude of sins.
It says, hi Jennifer.
Faith and learning.
Yeah. Oh, there you go.
Well, this is exciting.
Okay. So now is everybody?
I think I only get 7 tokens.
Well, okay, so empty for the start, right? Oh, no, you're right. Because that int1 and int2 are both
They're both
just,
integer.
they're both integer. Oh, you're right. You are right.
Okay.
Yeah. But another take back.
I'm just glad I would have tonight. I'm like, 8? I don't have 7. Where's the 8th one?
No, because I was counting here and then I was like, oh.
Also, the next edition of the book, I'm going to make a whole lot more mnemonics. The website is the final specification, as opposed to what's in the book.
Right. The book's was a little.
It also says that we have to draw the UML diagram. Do we have to do that?
Oh,
Yes.
And turn it in on paper then?
Yeah.
on Monday.
Uh-oh. That doesn't sound like an easy time.
Well, we did half of it already, basically.
The UML diagram for the
It's the abstract sorter, right? Or abstract token, sorry.
We need abstract tokens,
Abstract-
specific tokens.
yeah, with the attributes.
Is that all we need? Or do we
Yeah,
need
I think that's
tokenizer
all.
too?
No. Tokenizer is not a class. I mean, it's a class, but a tokenizer. Tokenizer only has one.
We don't care about it.
No, it just has one attribute, and that's the buffer.
We can add methods to util, right?
Yes, and now I put util in there for you to add methods to it.
Oh, like we did in our other.
Oh, I added so many.
assignment.
Oh, did
So
you?
many.
You added some of these.
Yeah.
Can I
made-
mention
made a
something I
utility
figured out
that will
that's helpful?
give me a Boolean value if it's
Yes.
out of the range.
Oh, yes. See, it's really good to, that's the other thing is that a lot of you guys had a lot of extra, well, I guess the reason you had extra coding is because you had all those unnecessary states, but anyway. So yeah, did you have a tip?
Yeah, I realized that if you're in a final state and you're kind of looping on that state, you don't need to say state gets the state you're in.
Oh, correct.
You just don't say anything.
Correct, you don't say anything because it's already in that. Yeah.
I was typing that out and then I figured it out.
Good observation. So if you're in a state, you don't have to say state gets to stay in that state because the state variable doesn't change. So there's no reason to unnecessarily assign it to itself, to its current value. You'd just be assigning it to its current value anyway. And also you guys realize about the backup input? Did you ever use the backup input?
Yes.
Good.
And a
Because you
lot.
have to.
Yeah, and the design rule is, or the design principle is that if you are in a final state, you can never fail. Right?
Right. So you never need to.
You can never fail if you're in a final state.
That's just the design of the tokenizer.
No, well that's it,
Yeah.
any multiple token recognizer. Are you with me? And why is that?
If you're in a final state.
Because if you're in a final
something
state
that's weird.
and you get something and you don't have a transition from that state
Yeah.
on that character,
Then-
then you know you've gotten something legal and you back up the input and let that be processed for the next token. That's why we have backup input. Are you with me? And until you've seen this done, you can get really ugly, bad code. You can say, oh, what's the next character? Oh, if it's this, I know it's going to be this. And then you can start making decisions within that case to look ahead, and things get all...
Oh, yeah.
You understand what I'm saying? They can get really ugly really fast. To go and look at the next character. Oh, if this next character, then I can jump to here or whatever, but then...
You stop being
You stop being systematic.
So it can be any.
So like, on the board, probably had comma LDA. That's not an addressing mode, but that's okay for now.
But for this, it will say it is.
So technically, we can have any, like,
You can have any identifier after the comma.
that would be considered an address in the.
And then
Yeah.
when we make our grammar.
And it's only whenever you do the parser that you will discover
But that's false.
that it's an incorrect addressing mode.
So basically, we could have.
But the lexical analyzer doesn't know.
I mean, it could have my name, and it would think that. it's
Sure.
I would think it's an
That's why I was
addressing mode.
confused how we could do that all with one state to check like the essay.
Well, okay, so, and this is really good, this is a really good observation, because now you understand the distinction between a tokenizer, in other words, the lexical analyzer, and the parser. The only thing that the tokenizer does is recognizes strings of valid tokens.
It just checks
It-
syntax, essentially.
Right, well, it's at the lower level of abstraction. Its input is a sequence of terminal characters, and it just recognizes the meaning as a group. The next string of characters has meaning as a group. Once it figures out, oh, this has meaning as this group, boom, there's your token. It recognizes it,
Parser
ships
takes
it on.
tokens
And then the
valid
parser,
tokens.
yeah, and then what the parser is going to do is it's going to take the string of tokens, and then it will figure out that this is incorrect. Because what you have to see, within the token will be the information of, like within the addressing mode token will be it should have, well, no, inside the token itself, inside an identifier token will be the string.
Right,
That will be an attribute.
right.
And so the parser will be able to have access to that attribute. Are you with me? And so it can say, oh, it claims this is an addressing mode. And then it will do a table lookup to verify that it is, in fact, a valid addressing mode.
And that's going to be the next part of this project. And we're going to use this exact thing we're building now with it.
This is exactly the way, yes, this is the first milestone of your project. And this finite state machine, this lexical analyzer, is what you will use. It's designed to do exactly what you need. Okay, are we good?
So creating classes for the address was the right way to do it.
Yes. 'Cause you need
Yes, there is an addressing mode. It should be T addressing mode.
Okay, gotcha.
What if I just called it ADDR mode?
Whatever. But just don't call it X.
Oh. T. Oh.
And start them off with T's. On the next edition, I'm not going to have this E or
I was
this.
gonna ask.
Yeah,
What,
Yeah, that E, in C++, that's an enumerated type, and I don't.
What is the LS? Then?
No, the LS is that's the lexical states.
Okay.
Because what's going to happen is your not the lexical analyzer, but the parser. That's going to have another finite state machine, and so that'll be PS for the parser states. Okay, so that's another good thing about software engineering is we want to think carefully about what you name your naming convention is really important.
do you want us to name it these then, the LS?
Yeah, you should. Yes, definitely, but don't do the lowercase e.
Don't do the
Get
E.
rid
Don't
of
do the.
lowercase e?
Oh, no, that's easy to do. Listen,
Wait, is there a find all?
don't even use find all. In NetBeans, you need to learn how to use your refactor.
Yeah.
Your refactor. It's really neat. In fact, you should be glad this happened so you'll know how to do this.
Okay.
In NetBeans, there's a refactoring.
There's a tab on the top that says refactor.
Yeah, and what you do is if you take that name go to your where is it defined? Is it in the enum?
It's in the.
It's in the states. You go to that states and you do refactor and you give it the new name, it will go throughout your whole thing and will find out everywhere that's used,
That's cool.
and it will change it in one fell swoop.
I didn't need that earlier. Except you still have to do it 11 times because there's 11 words up there with an E.
Oh, well, I know, but that's,
Where do you,
I mean, once you're in
Come on,
there.
Brooke.
No, she's right.
do you actually
Please.
change your states class and then say refactor?
No, I think you refactor, I don't know. I don't know the exact
We'll
steps.
figure this out.
But all IDEs nowadays, they all have refactor capabilities, and they are intelligent. It understands the language and it understands where that's,
I read that, actually I found that earlier because
I think we're just doing.
I named a class the wrong thing, so I went back
Yeah.
to change the class name, and it said
Yeah.
refactor, but I didn't know what that was. so I
It'll
didn't wanna
change,
click it.
it'll change like all of the constructors and every time.
yes,
And that would be
yeah,
helpful.
in the whole project.
The whole thing.
That'd be nice when we're copying down the code, like when you provide the code, because
We
you
always
go
have
and
to change
change
it
the
from
name
figure.
and.
Yes,
everyone-
yes, you need to learn how to use the refactor features of your IDE.
I named them like T identifier, no underscore, and then T dot command. So these were lowercase except for the D and the C and no underscore. Those are them.
So you're not
Do
capitalized.
the tokens have to be all capitalized?
Yes,
Oh,
like yes, those enum values.
Okay.
oh, no, those are
Well, I know these are states, but on the example,
Tokens?
yeah, in the example that we did, we did the example the other day.
It's T identifier and T integer.
Here.
and-
They're not all capitalized.
They are.
The classes?
No, not the class.
I don't think they are in.
Well, look, come on.
I'm confused.
States are capitalized, all capitalized.
Wait.
That's a different one.
I think you're going to the right. That's,
Oh, sorry. These aren't enums. That's right. These are not enums.
These are classes.
These are classes. So no, it should be like it should be like as in figure 7.38.
Because in C++ they're names. Is that why these ones?
Yes.
Yes.
Yes. That's why. Oh, no, wait. I take that back.
So the R.
No, I'm sorry. No, I'm sorry. In C++, they are going to be,
They could be.
no, they are going to be subclasses because it is abstract token. But I think that might have been, in the next edition, they'll be, oh, no, wait.
When's the next edition?
The next edition, it'll actually tell you to do classes instead of enums.
No, wait, what's enums?
It says enum token.
It says
and then
define
has
tokens with enum.
E capital T and then all capital.
For, what?
The different
How could
tokens.
that have been?
Website for 11.
That's why we didn't know if they had to be all caps. Because aren't they just the tokens?
The enums are tokens in the book?
Yeah, that's why I was so confused earlier.
Yeah, I can see why you were confused now. Man, that's,
Is this a typo?
They say in the problem.
Do you want to see it?
it might be.
I think it's said to name it other.
That's why I was asking Brett why.
It might be. I think it might be.
What?
It is.
Yes.
What is?
Typo.
It is typo. On page 386. That is from a previous,
Is that the second typo you found?
It's a third.
In the book, it talks about the enums being, it talks about the tokens being enums. That's from an old version. Because in the text of the book, they are classes. Yeah. Oh, that's horrible.
Whew.
Is that correction not on the errata sheet?
The errata sheet? Let's find
Feeling
out.
lucky.
If not, you get points.
It's
Now I see why you were so
when I don't
confused.
understand stuff is why.
Yeah. Now,
Page is that?
what page?
86.
Is there an errata for page 386?
Ooh.
Okay, you get bonus points.
Boy.
Another typo.
For the third time?
Wait, what?
All right, I think we have beat this horse to death. Any more questions before we quit? We're all set? Okay, good
Is
deal.
that all we needed to do today?
See, yeah.
Let's just discuss.
Yeah.
so the point of that was just saying the tokens are classes, not enums.
So these are
Correct.
classes.
Correct. Just like Java. Go by the Java slides.
Okay.
Yeah.
And he gave us a file that has some of those classes, but not all of them. You'll have to make some new classes.
Well, I gave you that example one that we went through.
Oh, is that what it is?
You know, that, I gave you that,
I took that and just modified it.
yeah, yeah. Yeah, sure, that's how you always do
Yeah.
coding. That's how I did the demo. I went to the
Website.
website and I Googled it and, anyway. All right, good deal. See you all on Monday.